Okay, today is day 8. We had 2 more days, and we're done with this unit. So it's continuing on with samples and surveys. So yesterday we did mostly samples, how to take samples. Today is going to be kind of a variation of samples and surveys together, just study methods, different ways of collecting data versus just taking a sample. So our learning targets is I can recognize bias in samples and surveys. So same thing as yesterday. I can use probabilities to make fair decisions and analyze decisions. And I can make an inference from sample results. So inference might be a new word for us, but we'll talk about that. So there's 3 different study methods. So yesterday there were 4 different ways to take a sample, good and bad. Now these are study methods, so a little bit different. One would be to take a survey. So select a portion of the population that most likely represents the population and ask them a set of questions. So that's kind of what we did yesterday with some sampling. Another one is to do an observational study. So this is different. Observational study is where researchers don't assign any sort of questions or choices. Subjects are merely observed. We say in the wild, kind of just watch what people do. They don't know they're being observed. They don't know anything's going on, and data is collected. Now, from this, when you do an observational study, you can only find correlation. You cannot find causation from observational studies. So correlation is like these 2 variables happen to go together, whereas causation is this caused that. So you can't, if you do an observational study, you cannot say this caused that. You can just say there's a correlation. These 2 variables seem to always appear together. Then the third one is an actual controlled experiment. So it's where researchers will divide the subjects randomly into groups. At least one of the groups is given no treatment. We call that the control group. So they're just like business as usual. How life was going to be for them. They keep going. So they have no treatment, whereas the other groups are given treatments. We can even do levels of treatments. Eventually, if you take AP stats or probability and stats, you'll do that. You might be given medication, and you may be asking, does the medication work? But also you want to know what level of medication. Is 5 milligrams enough? Is 10, 15, 50, whatever it might be? Which one seems to be the most effective? Here, causation can be made if it's a well-run controlled experiment. So observational study can only give you correlation, but a well-run controlled experiment can find causation. Okay, so what's the difference between correlation and causation? Here's an example. Okay, just kind of showing you what, if we make the wrong inference here, then what happens? So on the scatter plots below, I should say below, I'm sorry, it's right on the left. So the scatter plot on the left, that's this guy over here. Move up here. The scatter plot on the left, the life expectancy for each of 41 countries of the world is plotted against the square root of the number of medical doctors per person in that country. So they square rooted it just to make it linear. We'll talk about that actually tomorrow, about the linear part of this. But for every country, it looks like the more doctors you have per person, which in this case is the square root of doctors per person, the longer you live. Kind of makes sense. You have better medical care, things go up. But we may stop there and say, well, that's it. Doctors, if you want your life expectancy to go up, you need more doctors. Just get more doctors in your country. The people in your country will live longer. Well, the problem with that is having a good doctor doesn't make you live. If you have a good dentist, but you still don't brush your teeth, you're still going to have cavities, no matter how good your dentist is. Or, you might have the best cardiologist in the country, but if you keep eating cheeseburgers and bacon and you don't exercise, it doesn't matter how good of a cardiologist he is, you're probably eventually going to have heart problems. So, just to really hit that point home, here's the square root of the number of TVs per person compared to life expectancy. So this graph says if you want to live longer, buy more TVs. If you have more TVs in your household, get more. The whole country just needs to buy more TVs and will live longer. Well, obviously that's not true. So which study method did we use for this, though? Did we Did we do a survey? We just selected part of the population. Did we do an observational study where we watched just what happens? Or did we do a controlled experiment where we divided them into groups, we gave them a treatment? Well, there was no treatment here. No treatment was given. It was just, we looked at how many doctors there were per person compared to life expectancy for all these countries, and we put them on a graph. It really wasn't a survey because we didn't go through and ask, a portion of the population and all that. It wasn't a survey necessarily. It was just a fact, like how many doctors per person compared to life expectancy. We didn't ask for their opinions, and we didn't, that kind of stuff. So what study was this? This was an observational study. We just observed over the last, whatever year this was. It was a certain year that they did this study, but they just collected the data. They didn't ask anybody any questions. They didn't apply a treatment. So this is an observational study. I just misspelled that. Observational study. So, because it's an observational study, can either of these show causation? Remember, observational study shows correlation. We can't look at these and say that, yes, doctors and TVs make you live longer. It's not true. So neither one of these can show causation because they're both of them were observational studies. In fact, if you had to guess, what do you think is probably, we call this a lurking variable. What is actually the real variable here? What probably does cause life expectancy to go up? Which would also cause more doctors and more TVs. Well, it's probably how much wealth is in your country. If there's more money in your country, you're going to have more doctors and more TVs, but also the more money you have, the better food you can buy, the better health care along the way. Not just number of doctors, but you can actually go to the doctor when you're sick very early and get things figured out. So really, it's economic. The wealth in your country is probably the real factor, and you could go through and do some of that. But neither one of these, TVs and doctors, don't make you live longer. Doesn't matter if you have the best doctors in the world. Doesn't matter if you have the best TVs in the world. You're not going to live longer. Okay, so another example of this. So, in a study conducted at a high school in California, researchers compared the scholastic performance of music students with that of non-music students. Okay, and so the music students had a much higher GPA than the non-music students, which was the 3.59 compared to 2.91. On top of that, 16% of the music students had all A's, and only 5% of the non-music students had all A's. So does playing music, being able to play an instrument, increase a student's scholastic performance? It makes their grades go up. Okay, so think about that. What kind of a study was this? It wasn't a survey. We didn't go through and ask people questions and their opinions. Was it an observational study or was it a controlled experiment? Okay, so because we say, does playing music increase? I mean, it's a causation. We're looking for a causation. So was it an experiment? Was there a treatment applied? And there was not a treatment applied. We just watched. We sat back and watched. Students decided if they wanted to play a music instrument or not. Then they got their grades, and we collected the data. So this one, does playing music increase your scholastic performance? No. There's a correlation. It seems like, if you play music, you are probably going to get better grades. Those are correlated. They go together, but it doesn't mean that playing music is what caused it. Okay, so maybe it's that more intelligent kids want to play music or something like that. So that might be the underlying factor. We don't know what it is, but we can't say that the music, playing an instrument, caused you to be smarter. So what type of study was this? Well, this was an observational study. See if I can spell it right this time. Observational study. Okay, now let's flip it over. Let's talk more about experiments now. So the front side, we gave you some examples of observational studies. Now we're going to talk about a well-designed experiment. Okay, so a controlled experiment. There's basically 4 principles. Two of them we need to know. The number 3 and 4, I put them down just so you know them. Like, you probably thought, what about this? Why wouldn't we want to eliminate as many factors as possible? Well, you do, but we're going to study. The 2 we're going to be quizzing you on and assessing you on is the first 2. So the first one is there is a treatment applied. So there's some sort of a treatment that's given to one of the groups, at least one of the groups. This can be anything from medication to fertilizer to allowing more sleep. Could be the subjects, could be people, could be plants, could be animals, could be anything. So it just has to be something that's out of the ordinary. So like a group gets medication that the rest of the group didn't get, or some of the plants got fertilizer and the other one didn't. They all got sunlight, but one got fertilizer. Did the fertilizer help? The other group, known as a control group, does not get any treatment. So the group should be significantly large. You don't want really big groups. You don't want groups of 10. If you're going to do plants, you want like 200 plants in each group. And if you're doing people, you want large groups of people. 10, 15 people isn't enough. Number 2, the treatment is randomly assigned. You don't let them pick. Subjects don't say, yeah, I'd like to have more medication. I'd like to have the highest medication you got. We randomly assign it. Okay, so the randomness is what helps us decide if it really is, if it truly does help. Again, the 2 you don't have to worry about so much. You want to eliminate as many factors as possible. So, like, you wouldn't want to give the plants with fertilizer a lot of sun and the one without fertilizer no sun. Because that's another factor. Now, sun could be a factor, but if you have to give both of them the same amount of sun, the same amount of water, now those are eliminating those factors because it's the same for both. You want the only difference between the 2 to be the fertilizer. Okay? And then you also want to replicate it. So you don't want to just run the experiment once and say, hey, look at that, it all worked. You want to run it several times with different kinds of plants, all different situations. And if every time the fertilizer helped one group of plants and the non-plants, the plants that didn't get fertilizer, it didn't grow, you can say, yeah, it's the fertilizer's helping. So you want to replicate it several times, several different groups. Run the experiment, now run it again with a new group, now run it again with a new group, keep doing that. So if a study is well designed, you can assume that the results represent the entire population. Okay? So if it helped this group of plants, they're this kind of green beans, then all green beans of that species will be helped. If this cholesterol medicine helped all men ages 30 to 40, helped the men in your study from ages 30 to 40, it probably helps all men from ages 30 to 40, and so on. So if this is the case, you can make general conclusions or inference. So inference is like inferring that it applies to the whole population. So if it's a good study, inference would say, yes, it's good for everybody, if it's a well-designed study. Which type of study method is described below? Remember, we got those 3. Okay, so it's either a survey, it's an observational study, or it's a controlled experiment. Should the results be used to make a general conclusion about the population? So was it a well-run experiment, basically, if it's an experiment? So number 1, researchers randomly choose 2 groups of 10 volunteers. Over a period of 8 weeks, one group eats ice cream before going to bed. The other group does not. A treatment is applied. So that's your treatment right there. One group gets ice cream, one does not. There's your control group. Volunteers wear monitoring devices while sleeping, and researchers record dream activity. Okay, so you dream more when you eat ice cream before bed, or good dreams, bad dreams, whatever. So what kind is it? Well, I see there's a treatment applied. There's a control group. This is a controlled experiment. So controlled experiment. And now, can I make a conclusion about the population? Okay, so controlled experiment can show causation if it's well run. Well, it didn't meet the first step. There's a treatment applied. It says randomly chosen. They randomly chose them, so the treatment's randomly assigned. They didn't get to choose, but one thing's missing there. The groups need to be significantly large. So 10 volunteers, that's not good. So if they choose 2 groups from 10 volunteers, it's probably 5 and 5. Okay, so it's not good at all. So the results may be unreliable. So the results may be unreliable because the sample size is very small. So you want to have a good sized sample. Okay. Part B, students in science class record the height of bean plants as they grow. Okay. So you might be thinking, oh, plants, that's an experiment. The problem is they didn't apply a treatment here. There's no treatment. It's just watching plants grow. Okay, so that's an observational study. So observational study. That's an observational study. And the results are unreliable as we don't know what factors they used. So we don't know any information about factors such as the soil, what soil was used, how often was it watered, sunlight, fertilizer, anything else you can think of. So yeah, there's just too many unknowns here because we watch, it's just an observational study. You might be able to find a correlation, but you won't be able to find any causation on that one. Student council members ask every 10th person in the lunch line if they like the cafeteria food. Okay, so there's no treatment applied here, so it's not an experiment. They're not actually just watching them to see what they do. They're actually asking them a question. Now we're back to a survey. Okay, so we're to a survey. So yesterday, this is a survey. We're taking a sample. This is a sampling method. Would it be, what kind of sampling method was it? So we're asking every 10th person in the lunch line if they like cafeteria food. So you think, well, it's every 10th. That sounds systematic. People are randomly lining up in line. That sounds good. But the problem is, if you are in the lunch line, are you probably more likely to like the lunches? If you pack, it means you don't like the cafeteria food. So those people aren't being included in this. So this one is going to have some bias in it. Okay, so again, it's unreliable. Students that are in the lunch line are probably more likely to like cafeteria food. Another example, a pharmaceutical company asked for volunteers to test a new drug to treat high blood pressure. So people have to volunteer, but then of the volunteers, they're randomly assigned into 2 groups. That's good. The researchers will monitor the blood pressure of the volunteers for 6 weeks. Okay, so which type of study method does this sound like? So they have a treatment, they are randomly assigning it, so that's a controlled experiment. So a controlled experiment. Should the results be used to make a general conclusion about the effectiveness of the drug in a larger population? So it kind of meets all the requirements. It doesn't say that it's a small group. So if it's large enough groups, then yeah, it is good. So we can say yes. Might be some other factors. Yes, says what other factors might be considered when testing the effectiveness of this drug. They put them in 2 random groups, but medication, maybe you notice it affects different age groups. It affects different genders differently. I mean, there's all kinds of different other factors you might want to look at. So yes, this is good, but it can be improved. So it can be improved in ways, other factors, age, gender, your previous medical history. So like if you already had high blood pressure, maybe it'll help you more than someone who doesn't have high blood pressure. It only helps you have a problem or something like that. So what was your prior BP average? A lot of things to consider there, but it is a controlled experiment. It does follow all the rules, but there's always a way to improve it. So if you were actually running experiments, you want to find the best. You want to eliminate all the factors that you can.